next we're going to start the mesh for simulation.
Okay, so I'm back because I didn't name. Okay, I'm gonna name these sections. So I'm gonna name this velocity inlet. Lowercase. This is gonna be, oh, let me just click edge. This is gonna be the pressure outlet. Okay, I'm gonna go out. These two are gonna be our symmetry. So I'm gonna go to symmetry. Okay. And then this is gonna be our wall. It'll be insert here. Okay. And then I'll go ahead and save this to my project and then update it. So I'll save the project. I'm gonna exit this once it saves. So exit. Okay. And then I'm gonna go back to, because this is for laminar and turbulent because I'm gonna use the same mesh and also the same names as well. So I'm gonna go ahead and update this so it has the names for all of our sides. Okay, that's updated. I'm gonna go ahead and finish these two. I'm gonna use the exact same mesh for both of these as I did for the first one. So this is our velocity streamline for laminar flow. You can tell that this is the sorry, the velocity for over a cylinder for laminar flow, because our velocity at the inlet is low, and then is low for this case, and then sorry, I'm just can't feel it in the air. Let me cut this out anyway. Okay. I know I wrote this somewhere. Okay, so for laminar flow, we know that our velocity at the inlet is the highest for laminar flow, and at the top, nah, that don't make sense. Okay, this is the velocity this is the velocity this is the velocity streamlines for laminar flow, and you can tell that this is for laminar flow because we have our wake region right here as well, and it's not as closed off as my turbulent one will be once I run that simulation. And that's all I needed to say. So I'm gonna start the simulation for turbulent flow. So I'm pretty sure I'm gonna set this to laminar, because laminar is where you get that. When our Reynolds number is greater than 500,000, that's when we get turbulent flow. So I'm gonna go here, and then I'm gonna go to fluid. There's a fluid is air, so I'm gonna set that to. I actually need to go to materials first and edit air. Sorry, and then I want the air density to be 1, and then the viscosity of air is 1.8, just like I did with laminar flow. So change and create. Close that. I have to make sure that our surface body is air, so I'll apply and I'll close that as well. And then I'll go to boundary conditions. At the inlet, I have a different inlet velocity. The velocity for turbulent flow is 36 meters per second. And that will give me a Reynolds number of 2 million. So that'll be 36. Maybe not 36, 1 second. So I wrote it down. Let's see. It is 36. It is definitely 36. It is 36 meters per second. I was just making sure. And I'll close that, and then our tuner surface body. I'll just hit apply and close to these because I'm really not. Our outlet pressure is just going to be 0, which is our gauge pressure, so I won't change anything here. And I'll close that. Our symmetry, okay, nothing to change about symmetry. And our cylinder wall, which is this, the outer edge of the circle, isn't stationary, so it's not moving, so I'll apply. And then I'll go to reference values, and we are going to calculate it from our velocity inlet of 36 meters per second. And then I'll go to methods, and methods, I'll do a coupled flow, and I'll just do this Presto. I saw a YouTube video that might be better. I don't really know because never mind. And I'll go to residuals, and I'll just add 1 0. I did add 1 0 for the residuals to each case, each simulation. And then I'll go to initialization. I'll do hybrid initialization, and then I'll set this to 25, and then I'll apply that, and it should save. So after I'll initialize. Once it finishes initializing, it shouldn't take that long. Once that finishes, I'll go to run calculation. And that is done. I'll go to run calculations, and then I'll do 1,000 iterations, and then I will come back once this is finished, because it will take quite a while to finish because I think my computer's running slow. I need to update. So I'll go ahead and calculate that, and then once that finishes, I'll get back on the video and show you the velocity and pressure contours, our velocity streamline, and our pressure coefficient plots, and our velocity magnitude plots as well. So I'll be right back. Okay, so now I'm gonna go ahead and I actually accidentally clicked the stream button, so now I'm gonna go to graphics, go to contours. I'm gonna plot the pressure contours at all of these locations, and I'm gonna enable contour lines. I've done this for all 3 simulations. I'm gonna save and display. And go ahead and close that, because this is our it's our turbulent profile for pressure. And now I'm gonna do another contour, and that'll be for velocity, magnet to velocity, and I have velocity magnitude. I'm gonna enable contour lines again and click all of these again as well. And I'll save and display that. I'm gonna go ahead and close that. This is our velocity contour for turbulent flow across the cylinder. Do remember that I chose the velocity for 36 meters per second for this simulation. And I'm gonna go to plots, XY plot. I'm gonna plot we'll do static pressure. We're gonna do the pressure coefficient at the cylinder wall, which is the edges of our cylinder that we have here. And then I'm gonna go ahead and save and plot that. This is our pressure coefficient plot. I'm gonna go ahead and save that. Oh, why the heck is it? Okay. I'll go ahead and save that, and I'm going to show you the velocity one as well. And that'll be at the cylinder wall as well. I'm going to save and plot that. Our velocity is at 0. And I'm going to save this one to my files as well. So I'll do the same name. Okay, I'm going to save that. And then I'll show you the velocity along the curve length, which should be at our cylinder wall. Okay, at our cylinder wall, which should be a little different. I'm also going to save that one, so it's the same. The velocity magnitude across the curve length and the velocity magnitude along the direction vector are the same. And I'll do the pressure from the pressure coefficient along the curve at our cylinder wall. And I'll save and plot that one. That one is a little bit different. I'm not sure why though, but it is different. I don't think I need that. But this is a good indication that our pressure at the wall is way different than our velocity along the curve length of the wall. So that's good. And then I'll go ahead and close that. And then I'm going to go to results and show you the streamlines that I have. And that'll be for turbulent flow. I'm going to go ahead here because I do have to take this. Okay. Once this loads, it'll take a minute. So. Okay, it's loaded. I'm gonna go here and click streamlines. I'll just make one streamline and it's across a surface streamline. And we're going to choose symmetry 1, which is this entire field here. And I'll choose 400 points. They're equally spaced and the variable's velocity. So this is our velocity streamline. So I'll go ahead and apply that. So this is our velocity streamline for turbulent flow. It should be a little more, the distance in our wake region should be a little more closed than for laminar flow, which you can see here because my laminar flow streamline is a greater wake region than for turbulent flow. So that is our streamlines for our velocity. I'm gonna go back to Fluent and I'm gonna get the drag coefficient along the cylinder wall, and I'll print that. We can see that our drag is 0.01, which is good for turbulent flow, 0.011, and then our pressure coefficient is slightly different. So I can go ahead and write that down. So I'll do 0.01, 0.169, and then our pressure 0.0120544. And then I also have to show you guys the drag for laminar flow, because I forgot to show you that. So I'm gonna go ahead and exit here because cancel. No, I need to take some screenshots. I will clip this out, but I am gonna take the screenshots of my plots, my contours, and my streamlines, just so I can have them. I don't want to I want this to be, this is good. That is good, so you can see that it's not symmetric. So I'm just gonna go ahead and print my screen right here. Oh, this is gonna be different because I didn't do it like this last time. Okay, that one's good. I'm gonna go to contour 2, which is our velocity contour. I'm gonna go ahead and display that and take a screenshot. This is good. You can tell that our pressure, the velocity is higher at the top and lower at our destination points. So I'm going to go ahead and I know how close it needs to be. That's why so you can actually see it. That's not. I wanted to see the whole graph, so maybe I have to come back and get so I'm going to get that. I forgot I was on freaking Twitch. I'm gonna go ahead and close. And I'm gonna go back to this and take a screenshot of my streamlines, which is actually good. I wish I had the straighter turbulent streamlines that everybody else has, but that ain't the case. That's not the case. Okay, that is good. And I'm gonna go ahead and exit that. I'm gonna exit this as well because I don't really need this no more. I have to go back here for laminar and get the pressure. Things I have close or something. I don't know why. Huh? I don't know why this. Please do not say fluid. Something not. Like, I don't know why they keep doing that. Thank you. See all my plots was here. Plot. Oh. Okay. I already need that. I'm gonna go ahead and go here. And get the drag, because I didn't get it last time. Okay. Our drag for laminar is 0.3137508. And then the pressure coefficient 0.30975431. And thank you for coming to my TED Talk. I'm actually done. I'm gonna close this shit out. Now I gotta stay here for hours and look at a freaking screen and edit a video. I'm submitting this shit tomorrow. Thank you. I'm gonna go ahead and get out of here. I'm gonna go ahead and close that. Yes, save it first and then close it for me. Thank you. Oh, thanks. I don't even know why I'm... Why is it doing that? Okay, I'm trying to figure out this. Okay, that's for a different class. Okay, cool. I gotta stop recording this.